Now you are given this question, right? The question says that verify Green's theorem. Before your Green's theorem can be verified, what it means is that your line integral must be equal to what? Double integral. So meaning that we are going to solve this question using line integral, we get our answer. We are going to solve this same question using double integral, we are going to get our answer. So the verification is that this answer that we've gotten, are they the same? If they are the same, it means Green's theorem is verified. If otherwise, state it, Green's theorem is not verified. Now, first thing first, given this question, or you say generally, given any question on Green's theorem, write out your formula, write out the formula you want to work with. Write out the formula you want to work with, right? Now, first thing first, solution. The formula says that integral c all into bracket Pdx plus Qdy is equals to double integral r all into bracket partial derivative of q with respect to x, right? This is the left hand side and this is the right hand side. So this is Green's theorem. This is what Green's theorem is saying mathematically. Previously when we did the introductory video, we defined what each term means for the left hand side and the right hand side. Now let's solve our question using the left hand side, meaning the line integral. This is the line integral, while this is the double integral. So let's solve our question using the line integral. Using the line integral, I have integral c all into bracket p dx plus q dy. Now this thing is very easy. It is that you are just doing substitution. You are just doing substitution. From here, you already know that this is the formula you want to work with. Then from here, what are your unknowns? I have p unknown, dx unknown, q unknown, and lastly I have what? Dy to be what? Unknown. So what this means is that by the time you know quantity of each parameter, say p, dx, q, and dy, you are going to substitute and you make use of the formula, right? But have it in mind that if you want to use line integral, we are using line integral first. If you want to use line integral, you are going to represent your question with a graphical illustration. Let me repeat that. From here, you want to start with line integral. Just that for any question given to you under Green's theorem, that question you are going to represent it graphically. What you are trying to do is that when we stated Green's theorem, we said Green's theorems relate a single closed curve C bounded by the region R to a double integral, right? So from there, what I just take from that statement is that illustration of Green's theorem. This is the illustration for Green's theorem. Say this is x, say this is y. Then graphically, we are saying that we have a single closed curve C. We are saying that we have a single closed curve, right? This single closed curve, the region inside is what? R, right? What is bounding this R? This R is bounded by what? C. This R is bounded by what? C. So now, what this is saying is that this is Green's theorem graphically, right? This is Green's theorem graphically. So what this means is that this is Green's theorem graphically. Right? And this is Green's theorem by formula, right? I'm implementing this formula. Just like the same way you are making use of this formula, you are also making use of this. So what this means is that this given question, you are going to represent it graphically. Now observe, from Green's theorem statement, we said we have a simple closed curve, right? This is just a curve. What this curve means is that it varies. In some cases, it might be square. You might have it as square. You might have this curve as square, triangle, right? And etc. Now check this question. What this curve that I'm having here, What shape is it? Triangle. So meaning that representing this particular question graphically, the expected curve you are going to have, in this graph will be what? In form of what? Triangle. So that's what it means. Let's say the question says that a square, if it was square, the expected curve here will be what? Square. But for me, I'm having what? Triangle. So what it means is that from this question, the expected curve here is what? Triangle. Now, the question is, this triangle, how am I going to bring it out? Just like we doing our normal x and y graph. Just like we do what? Our normal x and y graph. How do we plot this triangle, right? It's just like we doing our normal x and y graph. Let's say we have our graph sheet in this manner. Say this is x. Say this is what? Y. This is positive y, negative y, positive x, and negative x. And I'm given that A is 0, 0, B is 1, 2, and C is 2, 1. Let's say 2, 4, right? So this is of course I have 0, 0 with the origin. This is 1, this is 2, this is 3, this is 4, right? Similarly, I have 1, 2, and 3. Now from here, for A, this is x, right? This is x, this is y. This is x, this is y. This is x, this is y. Now let's say you are given this question. I want to represent each vertices or each coordinate on this graph. I want to represent each coordinate on this graph. How do I go about that? That would be what? For x, I'm having what? For this first one, I'm having 0. For A, I'm having 0, 0, meaning I have A at this point, right? For B, I'm having 1, 2. X is 1, y is what? 2. Now let's trace. For x equals to 1, I have it in this manner, right? For y equals to 2, I have it here. Meaning, representing your coordinates on this graph, you have something of this, right? This point is what? B, meaning 1, 2. Similarly, for the last one, for x, I'm having what? 2. Then for y, I'm having what? 4. This is x, right? Then y is what? 4. So I have my coordinates at this point. Then at this point, I'm saying that I have C. What's the coordinate of C? 2, 4. Mathematically, this is my representation, right? So same idea, nothing is changing. I'm replicating this guy. I'm using this idea to plot my what? Right angle triangle, my triangle. You know, from this theorem, I know that the expected curve that I'm going to have is what? Triangle. The question is, how do I plot this triangle? Adopt this idea. That's what I'm going to do. Now, to plot this triangle, if you go back to that question, you are giving vertices, right? Yes. Now, what are these vertices giving? What are these vertices giving? I have that 0, 0. I have 1, 0. I have 1, 1. So nothing is changing. Using this idea, let's plot our triangle. So that becomes, first thing first, have your reference line for y and x. This is my x. This is my x. This is my y. Now, let's say this is 0. This is 1. Let's say this is 1. This is 2. This is 2, and this is 3. Then for this, I have one, I have 2. Now from here, let's plot these vertices to get my triangle relating to this theorem. For this first one, say this is A, say this is B, say this is B, and say this is C. Now for A, I'm having what? 0, 0. So I have it at this point, meaning I'm having 0, 0. For the next one, B, that was what? Given x is what? 1, then y is what? 0. So I'm still having B at this same point. True or false? True. Lastly, I have C. Meaning for x is what? 1. Y is what? 1. So I'm having it at this point. Let's trace. Right? This is for C, meaning 1, comma 1. Now, the idea is that, this is point A, this is B, this is C. Now, from that question, we already know that I'm going to have the word triangle. I'm going to have the word triangle, meaning each point, join each point together with a straight line. Meaning from here, let's move in this direction. The first one is what? AB, BC, then what? CA. Then CA. AB, BC, then what? CA. Meaning from that question given, this is my curve. And you can relate this to what? Green's theorem. Because from Green's theorem, when we stated it, we made mention of what? A closed curve. So for this particular question, this is what? Closed curve. This is the closed curve. So now from this place, we apply this idea to this place, right? Now what we will be using here is that you are going to call each point segment. You are going to call each point segment. Each point whereby we have our vertices. We said this is point A, point B, point C. We are using points, but the appropriate word is segment. What that means is that earlier when we started, we said we want to make use of this formula, right? We want to apply this formula. This is line integral. We said we want to apply this formula, and using this formula, I need what? P, I need dx, I need q, and I need what? dy. This is what I'm going to use. From here, I'll be applying this formula to each segment. I'll be applying this formula to what? Each segment. I'm having 3 segments here. The first one is what? Segment A, right? The next segment is what? B, and the last one is what? C. Now, mathematically, this is Green's theorem. This is the line integral. This is the double integral. Using the line integral approach, it means you are applying line integral to segment A, you are applying line integral to segment B, and lastly, you are applying line integral to what? Segment C. And you are applying this line integral, you already know the unknowns that you are looking for. These are the unknowns. Meaning at each segment, you are going to find the value of these parameters, right? At segment A, I need the value of P, I need the value of dx, I need the value of q, and I need the value of what? dy. Now let's solve. Using line integral, I have integral Pdx plus what? Q dy plus Q dy. Now, the thing is that from here, what you should take note is that P and Q are the vector field. P and Q are the vector field, right? Then the x and the y, they are the derivatives. Take note that your dx and dy, they are the derivatives. Alright, he said the x and the y, they are the derivatives. P and Q, they are the vector field. Now check that question. What are the vector field giving? You are giving two vector field. Yes. You are giving the vector field to be what? You are giving that x square plus y square I plus x minus y j. Now in this case, your P is equals to x square plus y square, and your Q is equals to x minus y. Just take note that the one you have your I, this is the x direction and this is the what? Y direction. Just that I takes P, then J takes what? Q. Right? Now from here we said we are making use of this guy. We said P and Q are the vector field, right? We've identified it. We've identified the vector field. Just that for each segment, we are applying this line integral to each segment. Just now this formula, this vector field remain constant for each segment. Segment A, this is your line, this is your vector field. Segment B, this is your vector field. Segment C, this is your vector field. What varies is that this derivative, meaning the x and the y. And take note, this derivative, in differential in differentiation generally, before you can get a derivative, the function must have been given. Meaning I'm differentiating a particular function. I'm differentiating a particular function. Now, let's say that you are given that y, or you are given that m is equals to x. M equals to x. From here, differentiate. Meaning you are differentiating m with respect to what? X. That is, I have the m over the x to be what? 1. Cross multiply. What this means is that the m is equals to what? The x. The m is equals to what? The x. You know, in this case, I'm having m equals to x. Let's say this is 1. 2. Let's say I have p is equals to q. Differentiate as well. I have that the p over the q is equals to 1, which implies that the p is equals to what? The q. Any question? The same way we did for 1, that's the same way we are going to do for what? 2. Now, what this means is that to get the x and to get the y, there's this particular function that I'm going to differentiate. There's this particular function that I'm going to differentiate, and this function is usually represented as t. Is what represented as t, and not just t. It's actually called parameterization. Meaning that from this parameterization, there's a formula to calculate for y and x. Let's say you have that, you already agree with me that this function that we are referring to is what? T, right? This function we are referring to is what? T. Let's now say that I have that y is equals to t, and I have x is equals to what? T as well. Now from here, let's differentiate. By the time we differentiate, what do we have? The y over the t is equals to 1. Cross multiply. Not like the way we did here. The y is equals to the t. Similarly, I have that the x is equals to what? The t. But the question is, how do I get this t? And how do I, this is a function of y. This function of y, when I differentiated, I got the y, which is the unknown here, to be the t. This function of x, I got as t. By the time I differentiated, I got the x to be what? The t, which is the unknown here. Now, what this means is that there's a formula to calculate for y function, and there's a formula to calculate for what? X function. So this is where this word parameterization is coming from. And this formula is that for y function, this formula is giving us y is equals to y1 plus t all into bracket y2 minus y1. For x function, this formula is giving us x1 plus t all into bracket s2 minus x1. Now with this formula, once I've gotten the y function and the x function, I'll be able to differentiate. By the time I differentiate, I know the value of the x and the value of what? The y. And I'm going to make use of this value that I've gotten at any segment I have. If it's segment A, segment B, or segment what? C. Alright, with that being said, from here, let's see how we can apply line integral to each segment. Let's see how we can apply line integral to what? Each segment. Segment A. Applying line integral to segment A, I'm using this formula. I need my what? I need P, Q, the X, and the Y. Then for me, I said P and Q remain constant. P and Q what? Remain constant across any segment. Now, let's substitute. For segment A, I have that integral. Let's substitute our function of P. That becomes what? X squared plus Y squared dx plus my Q is what? X minus Y. Then dy, right? But in this case, I can, from here, I'm meant to know what? The x and the y. I'm meant to know the x and the y. Now, how do I get the x and the y? From our previous explanation, we said before you can get the x and the y, it means you must differentiate. What are you differentiating? You are differentiating the function of x and the function of what? Y. Using this formula, let's get the function of y at segment A. Using the same formula, let's get the function of x at what? Segment A. But you observe something from each formula. Call this one, which is for y, and call this 2. For 1, which is the one I'm going to use to calculate the function of y. To work with this, what are the unknown? y1 and y2. Right? y1 and y2. Any question? From here now, I have to make use of 1 and 2 to get the function of y and x. But you observe something. To use this 1 and 2, I need y1, y2, x1, x2. Meaning from here, I have the unknowns to be what? y2, y1, x2, x2, and x1. x2 and x1. Now from here, how do you get? What this means is that you must know y2, y1, x2, x1 at each segment, right? You must know it at each segment. Why? Because you are applying this 1 and 2 at each segment. Now for these values, to get this value, you are going to move. From everything still lies on Green's theorem. We are still applying Green's theorem basically. What we've learned when we derive Green's theorem from the theoretical explanation of Green's theorem, that's what we are still applying basically. We said Green's theorem, if you can recall, in what direction does your C move? Your C moves in what direction? Counterclockwise. We said C is a positive oriented simple curve and it moves in a counterclockwise direction. When we say counterclockwise, what does it mean? Meaning anticlockwise, against your work clock. Now, from this closed curve that I have here, I want to move in a counterclockwise direction. Alright, let's do this together. I want to move in a what? Counterclockwise direction. Let's say you have A, C, B, call this one, and you have A, B, C, call this 2. Which one will give me counterclockwise? 1 or 2? AC. 1. Look at it very well. I want to move in a counterclockwise direction from this closed curve. 1 or 2? Which one will give me a counterclockwise? AC. Is it 1 or 2? 2. I'm moving in a counterclockwise, meaning against the direction of my clock. That is, I'm going like this, right? Let's say this is your work clock. This is 12, 1, 2. Okay, this is 3, 6, 9, right? I'm going in this manner, meaning I'm going against it. Going against it, meaning 2. That is A, B, C, D. So I have this. Let's say this is C1, this is C2, and this is what? C3. Now, how it works is that from here, this illustration, what it means that you are going to move in a what? Counterclockwise direction. You are dealing with 3 segments. Meaning that your movement will be basically 3 in 3 steps, right? Now, for the first one, I'm moving from A to B. I'm moving from what? A to B. The first one, let's do this together. The first movement is what? From A to B, and that's what? From A to B, what are the vertices or you say coordinates that you are seeing? I'm seeing 0, 0, 1, 0. Moving on, B to C, what am I seeing? 1, 0, 1, 1. Then lastly, that's C to A, what do I have? 1, 1, 0, 0. This becomes your movement. Meaning that to get the function of y and the function of x, these are your y1 and y2. These are your y1, x1, x2, y2. You are going to apply this in segment A. Take a look at this value. You are going to apply this in segment A. You are going to apply this in segment B and apply this in what? Segment C. Any question? I'm applying the first movement, which is C1. My movement, I've denoted it as what? C1, C2, C3. So the first movement, meaning C1, I'm going to apply it to what? Segment A. C2, meaning B to C, segment B. Lastly, C3, that is C to A, segment what? C. So that's how it works. Now, what segment are we? Segment A, B, or C? Segment A, meaning that I'm dealing with this. For now, this is my interest. 0, 0, 0, 1, 0, right? This is my x1, this is x1. From here, this is x1, y1, x2, y2. Implementing equation 1 and equation 2 that says that y equals to y1 plus t all into bracket y2 minus y1, and x equals to x1 plus t all into bracket x2 minus x1. Right? Now let's solve. Let's substitute. From here, my x1, let's x1 is equals to 0, x2 is equals to what? 1, y1 is equals to 0, and okay, from here, let me write it here. X1 is equals to what? 0, x2 is equals to 1, y1 is equals to 0, and y2 is equals to what? 0. Now let's substitute. Let's get the function of y. Y becomes what? Let's substitute. Substitute. We have 0 plus t.
No, it's 1.
Okay. This is y1.
Yeah, 0 plus t.
0 plus t all into bracket
0
minus 0, right? Therefore, y is equals to 0 plus 0, which implies that y is equals to 0. Now, equation 2, meaning x equals to what's x1?
0
plus c all into bracket 1 minus 0. I have that x is equals to what? C. I have x equals to 0 plus t, which implies that y x equals to what? C. Meaning this is the function of y and this is the function of c. Back to the unknown, I need the x and I need the y. By the time you differentiate the function of y and you differentiate the function of x, you are going to get this unknown. Starting with x, I have x equals to 2. Let's differentiate, meaning the x over the t equals to 1. Cross multiply, meaning the x equals to what? The t. Similarly, I have y equals to 0. I have that y equals to 0. Now, by the time you differentiate, you want to get the y. The y is equals to what?
0.
This implies that the y is equals to 0 because there's nothing I want to differentiate here. Y equals to 0, the y equals to what? 0. Now, let's substitute. Now, from here, I've gotten the y and the x. Let's substitute. Still on segment A, meaning my line integral all into bracket x square plus y square. In place of the x, what do I have? I have the t. Then plus all into bracket x minus y 0, right? Now from here, let's say this is 1 and say this is what? 2. You know, 1 is still the same thing as 2, but in this case you are differentiating with respect to t. All your integral function must be in respect to what? T, or not necessarily t. What you've gotten as x and y, substitute. From here, the function of x and the function of y that we've calculated, substitute into equation 2, or you say integral 2. Now let's do that together. I didn't know that x is equals to t and y equals to 0. Now let's substitute. I have integral t squared minus 0 squared, okay, plus 0 squared dt plus c minus 0 0. This cancel out, right? I'm left with what? Integral t squared plus 0 squared dt, which implies integral t squared dt. Now from here, segment A, after solving, I got this. The next step is what? Integrate. But for me, I won't integrate directly because what we are working with is a definite integral. You know, from differentiation, we have our normal differentiation and definite integral. What's the idea behind definite integral? The difference is that, let's say you have integral f of x dx, say this is 1, and 2, say you have integral a b f of x dx. Which one is definite integral? Between 1 and 2, which one is definite integral? 2 is a definite integral. Why is it a definite integral? Why is it a definite integral? Because I'm having limits. I'm having the lower limit and I'm having the upper limit. So in essence, what it means is that I'm going to use segment A to get lower and upper limits. Get the lower and upper limits. Similarly for other segments. Now, how do we get this lower and upper limit? How do we get this lower and upper limit? Now, you are making use of the vertices of each segment. You are making use of the vertices of each segment. Now, for segment A, what are the vertices of segment A? I said we are making use of the vertices of each segment, right? This is the segment. This is the vertex of what? Segment A. So with these vertices, I'm going to use these vertices to get, he said vertices or he said coordinates. So I'm going to use this coordinate to get the lower limit and the upper limit. Now, how it works is that we have fixed coordinates and non-fixed coordinates. We have the fixed coordinate and the non-fixed coordinate. So you are making use of the non-fixed. You are making use of the non-fixed. Whichever coordinate that is not fixed, that's what you are going to make use of. Now, what's the idea when we say fixed coordinate and non-fixed coordinates? Now, from here, this is, I'm having x and y. Let's group it by saying that x, all into brackets, x1, x2, and y, all into brackets, y1, y2. Substitute x1 and x2, similarly y1 and y2. X becomes what? 0, comma what? 1. Then y, what do you have for y? 0, comma what? 0. Now, we say this is a and say this is what? B. To get my limit, it is between a and b. To get my limit, it is between what? A and b. But I'm making use of the one that is not fixed. I'm using the non-fixed one. Is it A that is fixed or B that is fixed? We don't know. How do we identify the one that is fixed? So the one having the same value is the fixed coordinate. The one having the same value becomes the what? Fixed coordinate. Now identify, is it A or B that is fixed? B is fixed, meaning the y coordinate is fixed. Hence, your integral, okay, from here we said x is what? Non-fixed, right?
Yes.
And y is what? Fixed. Meaning I'm making use of this, which is what? 0, 1. Now the proper way to write this is that, since morning we said there's what we call parameterization. And the function of parameterization is represented as what? C. Is represented as T. Now, from here, what this implies that T is an element of 0, 1. T is an element of 0, 1. Any question? Right? What this means is that having identified the one that is not fixed, which is your limit, meaning the proper way to write it is as T is an element of 0, 1. Now, back to what we got here. It means that from segment A, I got this, right? I would have integrated, but I don't have my what? Limit. So introducing this limit, meaning I have integral T squared dt implies integral, your limit now, 0 to 1, T squared dt. Now let's integrate. Apply the idea of integration, meaning T squared plus 1 over 2 plus 1. Substitute your lower and upper limit 0 to 1. So you have T cubed over 3, 1 to 0. Substitute, meaning 1 cube all divided by 3 minus 0 cube all divided by 3. And this gives us 1 over 3 minus 0, which is equals to what? 1 over 3. Now, applying the line integral to segment A. I got 1 over 3. Now we are going to apply this same line integral to segment B and to segment C. Then once we are done, we are going to sum up all our answers. So this answer must be the same using double integration. Once they are equal, it means this theorem is verified. If they are not equal, this theorem is not verified.